I'll tell you the story today about the development of the Thunderstorm Asthma Warning Service, which is about 7 years old now, and also a little bit about the science, but we'll start with the service and tell the story. So how many people can remember the event that happened on the 21st of November, 2016? Put up your hand. Okay, that's almost everybody, a few people too young for that. But how many people were affected by it? Your son? Yeah. It was a serious event. There were ultimately 10 deaths from this event. Nearly 10,000 people showing up at the emergency rooms in the space of 30 hours. The hospitals didn't know what happened. It was kind of a mysterious event. A few people knew about thunderstorm asthma, but by and large, it was this giant mysterious thing that hit the population all of a sudden. The ambulances couldn't cope. The hospitals barely coped. Population didn't really know what to do. But in the washout of it, the health department was very sure that they didn't want to be in that position again. So let's talk about thunderstorm asthma and what it is. We don't really understand it very well because it's a rare event. Melbourne gets an event, a large event, maybe once a decade, not as large as the one in 2016. That was a whopper. But, something that sends, say, hundreds of people to the hospital or to the emergency room for help. What are the ingredients there? You need something that's allergenic. In this area, it's typically ryegrass pollen. Ryegrass is a sown crop. It's a fodder crop that's widely used in Victoria. You need some kind of mechanism for concentrating that pollen in the air so that you have a lot of it hitting people. We think that is related to the thunderstorm part of it and the outflows from thunderstorms, but you can get that same sort of concentration with cold fronts or sea breezes, but they tend to be not as strong. So that's why the thunderstorm asthma, the thunderstorm that goes with it. You need something to break up the pollen because a pollen grain is around 35 microns, microns. And usually your sinuses will, and your throat will take care of that. It won't go into your lungs, but if it bursts into little subatomic particles or submicron particles, that's what you can breathe in, and that's when you find yourself in trouble if you're allergic. And then you need, of course, a population to be exposed to it. So this is a schematic diagram that dates back quite a long time to an event that happened in Wagga Wagga that Guy Marks, who's a professor of medicine and respiratory health, worked with people in the Bureau of Meteorology. And this is still our best conception of what happens during thunderstorm asthma. It's relatively rare. The events that have been published are here on the chart, and you can see that down in Australia we're the hotspot globally, but also England is another place where you have to watch out, and there's been a lot of work done there. Other places, typically the Middle East, there's been one in Canada, a few others that are maybe not on the chart. I think there's greater awareness now, so we might start to see more reports of thunderstorm asthma. But a little bit more about the event that occurred in 2016. We've got on the left and the right charts two other events that occurred in 2003 and 2010 in Melbourne, which were big events for the time. And you can see the spikes in the number of people appearing in the emergency departments. The 2016 one on the far right of the left-hand diagram is just really much, much bigger than any of the others. And then if you look at a time series of what happened hour by hour, again, the red curve shows the 2016 event. In the evening, the other ones also were in the evening, and that's mainly because of the convection that happens during the afternoon to form the thunderstorm. So what were the environmental conditions leading up to it? It was a wet year. It was one of the wettest on record. So you can see in the upper left a rainfall chart that shows that in Western Victoria, it was pretty much, it wasn't the highest on record, but close to. And the pasture land is shown in the green chart below. So it was wet, a lot of grass, and a lot of pollen. The chart on the right shows back trajectories, or shows trajectories of where the air came from when it arrived in Melbourne. So you can see it's come from the north in hot northerly winds. and blowing over some of that pasture land, bringing some of the pollen into Melbourne. So that's probably the source of the allergens. This chart is showing radar imagery. So this is from the Bureau of Meteorology's radar. And the black line is the gust front. So that cold pool of windy, dense pollen air that's blowing out in front of the storm. And then behind that, with the asterisks that start out red and they turn yellow, those are emergency ambulance callouts. So pretty much within 20 minutes of that going past, you start to get people calling for the ambulance. And we've never seen anything quite so rapid before. Usually it's more like, I don't know, an hour or something. So this, we think that this event might have been special because it was a thunderstorm squall line. So not just one storm, which might have an outflow, which pools in kind of a puddle. This was a line of storms. So the only place the air could go was out in front. So it was a bit constrained, like a push broom. And we think that might have concentrated the pollen a little bit more. And just another meteorological chart just to show some of the other weather that was going on as that went through. The circled red spike is gusts. Those were very strong gusts. Lasted for kind of a long time for gusts, really. That normally lasts 10 to 20 minutes. And there was quite a lot of storm damage as well, trees and roofs and things that were damaged. And then in the gray bit, the temperature just plummeted, as happens in Melbourne cold fronts, right? And the humidity jumped up. So the government response in Victoria, first there was an investigation and then a set of recommendations. And so the two that I'll talk about in the talk today are the development of the thunderstorm asthma forecasting systems and then the applied research that was done in parallel to developing the system. I was really fortunate to have the opportunity to work on both of these things. In particular with the warning system, it's very unusual that a new warning system gets developed. It's, usually things get improved, but for something new to come along and to have an opportunity to be part of the development of that was quite exciting and maybe one of the highlights of my career, if I'm honest. So here's a bunch of health department and university and Bureau of Meteorology people sitting around a table thinking, okay, we've had this big event. We need a system to be working in less than a year. What are we going to do? And so necessarily it had to be something that was pretty simple, that wasn't going to require a whole lot of new technologies and new research and so on. We hope to do that, but not in the space of less than a year. So what we came up with was this risk matrix for epidemic thunderstorm asthma, where on the bottom, sort of going across, pollen concentration. So the more pollen you have in the air, the higher the risk. And this is grass pollen. We're not able to measure ryegrass pollen specifically without doing a whole bunch of genetic analysis, but we can at least tell when the grass pollen apart from tree pollen or other plants. So more pollen, higher risk. And then on the y-axis, weather risk. So what's the likelihood of getting severe thunderstorms with gusty winds and outflows? And again, the higher the risk of those thunderstorms, the higher the risk of thunderstorm asthma. So in the upper right-hand corner is what we called high risk. Without trying to put a number at it, we didn't know if it was a 50% risk, probably not that high, but was it a 5%? We just didn't know. It was sort of a relative scale. But the problem was if we, oh yeah, go ahead. We're not sure. We sort of think not, but we're not absolutely sure. So there are some theories in the UK that the lightning could be involved. More about that later. In order to know what was happening with the pollen, we needed to get some pollen monitors out there quick smart. So at the time, there were three. There was one at the University of Melbourne, which has been there for decades, one at Deakin University in Burwood, and one at Deakin University in Warren Ponds. And that's so just only in the Melbourne area. But the state health department wanted us to warn anyone in the state. So we needed to go out and purchase some equipment. What you see in the upper right is a Burkhardt pollen trap, and it's basically kind of a vacuum cleaner with a wind vane on it. So it orients itself to the wind, and then it sucks it in, and it's got a sticky tape with a gel that catches what's in the air. And you run that a day, you change the tape every day, and you take that tape, that sticky tape, into your lab and look at it under a microscope, and you count grains of pollen in the sticky tape. This is how it's done. It's not very I don't know, sophisticated, but it's the best that we had at the time. And I'll say a little bit more about automatic counters a little bit later. But so we had to purchase some more pollen traps. That wasn't easy to do. We needed to get them out there. We needed to find people to count the pollen. And it wasn't you can't just find pollen counters on the street corner. So we trained up people at universities across Victoria to do that. And so that's Penny in the on the left, they're training some students at one of the other universities. And I think I haven't learned how to count pollen myself, but when I retire, that's one of the things I'm going to do. We also then needed to predict pollen, because it's good to know what's happening, but ideally you want to know what's going to happen. So one of the people in the team was a statistician, and he took the pollen measurements from Melbourne over the decades and created a statistical model that related it to temperature and rainfall, relative humidity, and so on. And importantly, pasture fraction and vegetation state, because you need to know if the grass is actually blooming and emitting pollen. And so we needed satellite data to do that. But we were all astounded by how well this pollen modeling worked. So this is for Melbourne. The forecasts are in the red, and the observed are in the black. And you can see it's not quite catching the peaks, but it's getting the timing pretty well. And that's a forecast, again, for Bendigo. And we had 8 sites in Melbourne that we tried to predict this for. And then we had to turn that into a grid across the state of Melbourne using weather model data from the Bureau of Meteorology. So here's what the forecast looked like that rolled out. So we had a number of different partners doing their bits. So up in the green, the grass pollen prediction early in the morning, the University of Melbourne would run the statistical pollen model, and then they would do the counting under the microscope and use that to check the accuracy of the pollen model. And we did a little bit of tweaking of the model over probably several years to try and get that better and better. So the monitoring would happen at the 8 different sites around Victoria. That's the yellow. And then it was sent to the University of Melbourne for sort of a quality check, because so many of the counters were first-time counters, and they had biases and inaccuracies and so on. Then later in the morning, the Bureau of Meteorology would jump in. It would have a look at the thunderstorm outlook, make forecasts for that afternoon and the next 2 days. And then taking that together with the pollen forecast, which we would get from the university, find where in that risk matrix the risk should be. And we made these forecasts for 9 different forecast districts of Victoria, and I'll show you on that shortly. And then if there was anything to worry about, well, whatever it was forecast, we'd go to the health department, and then they would take it from there. All the warnings, the communication to the health departments, or to the health sector, I mean, to the community, hospitals, pharmacies, and so on, would come from the health department. It was their warning. So our advice from the Bureau was to the health department, and then they took it from there. So here's what you can get, and this is what it looks like even now. It's on the Vic Emergency app. You can also get it on the Melbourne Pollen app or the Department of Health's website. But you can see, maybe you can see there's sort of 9 different divisions of Victoria. And if the risk is low, well, it gets green. If it's a moderate risk, it's orange. And if it's high risk, it's red. So just for this particular day, Melbourne is in the middle, bottom middle. Our district is called Central District. You might hear that on the radio if you listen to weather forecasts on the radio. We're in Central District. And then you can click on a district and you get just a little bit more information. It's not very much more information, but this Vic Emergency is kind of a nice website. You can get it to send you an alert. If you're worried, you can sign up for flood or wind or other kinds of hazards. And of course, probably even more important was awareness, so public health education campaigns. And the Department of Health put a lot of energy into this. You can find videos on their website. They went out and spoke to school nurses, to pharmacists, lots and lots of different people. And so if you're interested in the topic, I would really recommend going to the Better Health channel on the Department of Health's website, and you can find all kinds of good resources there. And I think, you know, when it comes to people staying safe, I think the first thing is risk awareness, knowing that you are at risk, when you're at risk, whether you're at risk, and what to do about it. And all of this sort of education stuff is really aimed towards that. So how did our forecasts perform? This is a chart showing for all the forecasts. This is just Melbourne, their central district. The number of forecasts of low, moderate, and high on the 6 years that we've been able to evaluate. And the left-hand column is how many times there wasn't a thunderstorm asthma event, and the number of columns on the right is, or the numbers on the right are how many events we had. And they're not huge events, but events that we can identify. And so you can see, well, not great. You know, we hope when we get high risk, predict high risk, that maybe it happens, but actually it's probably good that it didn't happen. The moderate risk is about 10% of the time. So of 10 predictions of moderate risk, 1 out of those 10, it'll actually happen. And at low, it's more like 1%. So 99% of the times we predict low risk, didn't happen. So that's behaving how we would want it to. We don't have a lot of numbers, but we think we're on the right track, but really want to do some science to see if we can do better than that. So how many people remember another event that happened in 2020? Was a lot of media around this one. And this would never have happened before 2016, before we had this service. But the Bureau of Meteorology could see thunderstorms coming days in advance. It was the month of November, which is the month that we worry about the most. There was a lot of pollen around. And so the media really seized on this. We had joint conferences with Ambulance Victoria and the Health Department and so on. It was out on Twitter and all kinds of social media type stuff, Victorian Emergency and SES. And in fact, there was a big event that happened that day. There were more than 1,000 cases of call outs to the ambulance, 72% up from normal. If Ambulance Victoria hadn't been prepared, they would have likely been overwhelmed. So we don't know, you know, without all that media and all that warning and so on, how many people would have, more people would have gotten sick, but we're pretty confident that that made a difference. And some of the things that contributed to that working well was the joined up media, so proactive engagement with the partners. They collaborated, they didn't cross the wires or anything like that. They were all singing from the same songbook. And they really talked about the impact first. So they didn't say, oh, today lots of thunderstorms. They said, today, if you suffer from hay fever or asthmatic, you need to take care of yourself because you're at risk today. And so it's leading with that impact. Yeah. It probably did. Yeah. So just to sort of tie up what we've learned about thunderstorm asthma forecasting, so it's epidemic thunderstorm asthma. We sometimes abbreviate it ATSE. We know that we had a simple thunderstorm asthma risk forecast that was based on joint probability of severe thunderstorms and high pollen concentration, showed modest skill, not great skill, but modest. We found that usually the conditions that we thought would be dangerous didn't turn out to have an event. That's good. That's good, but it's just showing that it's really hard to predict. You know, you think this is a risky day and it doesn't happen. Definitely the awareness of, and the fact that we even had a service helped to keep people safe. And it's part of this overall strategy that includes preparedness, real-time monitoring and early detection, the warning process from the health emergencies, and the public awareness and education programs. So those are all continuing. The service is live right now. It runs from October to December every year. This is our last year of being a pilot. Next year it will be fully operational. But what can we do scientifically to see if we can do better? So we have a number of different knowledge gaps. These are just 4. There's more. But some of the questions that we asked ourselves were, what combination of weather conditions and grass pollen leads to thunderstorm asthma? Can physically based pollen modeling help? I mean, we were using a simple statistical approach. How can we better characterize the sources and the timing of the pollen? And then what causes the rupture into the allergenic particles? And can we model that? So we had a 3-year research program that was happening at the same time as spinning up the service. I was the science lead of the program, but we had botanists, statisticians, remote sensors. Who else was in the team? Air quality specialists. That was quite a multidisciplinary team, and it was really interesting and fun to work in that team. Oh, and a meteorologist. So yeah, this is an example of the kind of capabilities that we needed in order to do this work. So quite a lot of different skill sets involved in it. So the first thing that we had a look at was what can we conclude about the weather? We know that gust front, that nose under the thunderstorm, seems to be important, but how important is it really? And so some members of the team did a case control study where they took historical data and they asked a set of meteorologists who were retired and had a little bit of spare time to look at 10-minute radar data, days and days and days of this radar data, and identify if there was any convergence lines or where, gust fronts on the radar data. And then we put for a set of 15 days with thunderstorm asthma and 30 days without thunderstorm asthma, did some statistical testing of when there was one of those convergence lines within, I think it was within 20 kilometers of a hospital. Was that hospital more likely to have thunderstorm asthma than not? And it turned out that you just never got thunderstorm asthma unless there was a convergence line nearby. And so we were able to show that it's necessary to have the convergence line, but not sufficient. So that was already good to be able to say, okay, well, we know we need convergence lines. There's lots of ways to get convergence lines, though. You don't need a thunderstorm. Like I said earlier, you can have a cold front. You can have just, other kinds of atmospheric circulations, troughs, and sea breezes and so on. But the stronger. Yeah. Let me go back to this. Okay, so in this picture, we've got in the yellow, that's meant to be air with pollen in it. I should have explained. But you've got this outflow from the thunderstorm that's coming along like a puddle spreading out. And the air nearby it is still. And so you've got this air coming together, and that's the convergence line. So what you would typically get at a convergence line is the air needs to move, it needs to go up, it usually gets a bit turbulent and that kind of thing. So that's why you get gusts as well, because it's like a clash of air. And when you think about the word front, it sort of comes from war languages. So, the Western Front, that's where it comes from. Yeah. Yeah, so we know it's near the surface. Pollen's kind of heavy. It takes the wind, stirs it up. But yeah, we think that when in that convergence area, it's being compressed together somehow. Now there is some more theory that says that perhaps it goes up in the updraft. If it's a strong updraft, that can happen, and then it can come down in the downdraft, and it might break inside the cloud if it gets wet. So that's a very appealing sort of theory, and there seems to be now some evidence from some studies, which I'll show you later, that's suggesting that might be what happens in some cases.
More concentrated asthma in locally if one one theory is correct, the way that we generalised it with the other theory.
Yeah, yeah, that's
going up in sweeping over a very large area. It's only in the water that's going through with the
yeah. I strongly suspect there's a few mechanisms that can cause it. That it's not just one thing. We saw one event where there was just several days of very high pollen concentrations, and people didn't go to the hospital right away, but they sort of started wandering in a little bit later because it all got too much as that sort of a dosage effect. So we wouldn't call that thunderstorm asthma. That's just asthma. But yeah.
SARS event on pharmacists.
That's been suggested. I think there's probably groups looking at that. It's just getting that data can be a bit tricky. But yeah, I think that's a great idea. So the other thing that another young colleague was interested, he was actually interested in gusty winds and trying to help energy companies know when power lines were going to blow over and things like that. So he was looking at indicators of when you could get thunderstorms with gusty winds. And that's just the kind of thunderstorms that we were interested in as well. And he tested using atmospheric reanalysis. So it's basically a run of your weather model where you put in absolutely every observation that you can, and it's your best three-dimensional representation of the atmosphere. And he tried all different kinds of thunderstorm diagnostics, stability indices and frontogenesis indices and things that weather people would look at, meteorologists would look at. And it turned out that the best indicator of separating the cases with asthma from the cases without asthma was low-level moisture. And that surprised us because we really thought it was going to be these stability things. That's what our meteorologists use, which got us thinking. If there's a lot of moisture, maybe those pollen grains are popping down there. So we don't know for sure, but that could be part of what's going on there. So you sort of wonder, well, do we really need to worry about how much pollen there is? Maybe we can just use the weather. What if we just used the weather and didn't worry about counting pollen? Very expensive to measure it, count it. That's by far the most expensive part of the service. Bad idea, because if you use only the weather, you way overestimate. You get far too many false alarms. It's better than nothing, but it's not great. So we do think that we need to keep working on the pollen. So what I've got on here, that the left-hand table, and that's the original matrix that I showed you and the original results that I showed you. If we then take that humidity, that low-level moisture that turned out to be a good estimator, and we force another dimension into our matrix, and this one on the right, we can actually get better results. They're still not perfect, but they're better. So we're hoping to get a weather, pollen, humidity based matrix into our prediction system next year, hopefully. So a little bit more about measuring and predicting pollen. So here's some examples of satellite imagery from the Himawari satellite. That's our weather satellite that you get the frequent weather pictures from. And you can use the multiple channels to derive an index of the vegetation. It's using different bands in the infrared. It's a passive sensor, so it's looking at radiation coming up. And what you can get with this enhanced vegetation index is some idea of what the plant is doing. So I don't know if it's not that easy to tell, but each of these pictures on here is around, I don't know, a couple of weeks apart, maybe 3 weeks apart or so. And that one in the middle is a bit greener than the other. You can tell that. And when it's green like that, that maximum greenness, that's when the plant is getting ready to bloom. And so when you see that, then you think, okay, pollen's going to start happening in a few days. So that's what we were looking for, to see whether we could identify where and when the pollen was going to be emitted and make use of that information. Not quite. I'll come to that soon. That would definitely be an ingredient in it, is where and when is the emission of the pollen from the plant. So here's our grass map again, and we had to ground truth those estimates from space. And so this one of the postdocs on the project who was interested in what was happening on the land surface set up cameras in a few different spots around the state. So where you see phenochem on that left-hand side, the red dots, that's basically a time-lapse camera mounted on a pole pointing at the grass. Or, you know, it's often used for wildlife. You know, if you're trying to track wildlife and see what animals do at night or whatever, we pointed at the grass. And we used this to then tune the algorithm that was looking from space. So I thought that was pretty cool. Another area where some recent work is looking very promising is in the automatic pollen sensing. So there has been a recent study, international study, comparing all of the existing at that time automatic pollen monitors. And what these sensors would do, they would suck in the air and then usually use some kind of either fluorescence or pattern recognition to identify in the slide what's happening, how much pollen of different sorts are there. And so we were able to, or Ed Newbegin at the University of Melbourne, who's Melbourne's pollen expert, able to get one of these machines from Switzerland, the Pollino machine, and they're very happy with it. So on the plot on the right, well, they put both of them on the roof of the Redmond Berry building over at the University of Melbourne. So the Burkhardt trap that I showed you earlier, that's been there for yonks. And very trustworthy. It's a very reliable sort of thing. And you can see that this is really quite a good fit, and you know, our squared of 0.88. That's really good. So if we can get those machines to replace all those university students around rural Victoria, and continue to do the manual counting at Melbourne, because they count other things as well, but we could save a lot of effort and hopefully eventually a lot of money. Now, these machines are on the order of 200,000 each, but fortunately the health department's been granted some money to go and buy several of these. So we're looking forward to those. Well, I think they're probably out there. I don't know if they're out there now or if they're still coming, but anyway, soon. So that's been very encouraging. With the pollen prediction, another group at University of Melbourne, so related to the earlier statistical model, but they've gone much further with machine learning. And they've been using yesterday's pollen counts to keep tuning the model and as an input. And they've worked out that they can predict pollen, grass pollen, pretty much anywhere in Australia now, which is really good because it offers the opportunity to provide a pollen forecast service from the University of Melbourne, not from the Bureau. Pollen's unfortunately not our business. But yeah, so if you go on your Melbourne Pollen app, you might be able to find more information about this. And the accuracy of the machine learning predictions of pollen is greater than what we had with the simpler statistical model, using the same sorts of inputs. So just being a little bit more clever about how they're used, and recognizing it is still a statistical model. It's just a fancy statistical model. Okay, now here's some more physical modeling that you asked about. One of our colleagues at CSIRO was working with the chemical transport model. It's basically a dispersion in chemistry, air chemistry model that CSIRO has developed for air pollution purposes originally. But we could put pollen into this model and treat it as a pollutant. We called it PM35 microns. And we modeled the emission of the pollen using some relations that we found in the literature. Typically, pollen is emitted in the middle of the day when it gets warm. The plants sort of open up and the pollen goes into the air. And so what we see here are hourly maps of pollen concentrations from our model. Don't worry too much about the labels of low, moderate, unhealthy. Those are labels left over from the air quality forecast system that uses this as well. And so we were hoping that by knowing more specifically, more precisely where to expect the pollen concentrations to be greater and what time of day that if you could combine that information with more precise thunderstorm forecasts at this place and this time, you might be able to get more, pinpoint the more dangerous areas of the state. What we found when we compared the daily concentrations from this model to the statistical and machine learning models was it wasn't as accurate, unfortunately, but and funding finished. So this is I would say unfinished work. I think there's definitely scope to improve it, and I think this is where ultimately we'll go. But we'll need to get some resources if we want to do this. And then finally, trying to account for the pollen rupture. There was an interesting study that was done by someone in the United States who wasn't interested in health. He was interested in whether broken up pollen could be cloud nuclei, so seed the clouds. And so he was modeling the breaking up of pollen and getting carried up and to see whether you got brighter clouds when there was pollen in the air. But we used some of the relationships that he was using in his model to see whether we could replicate what happened on the big event in November 2016. Unfortunately, our results were pretty inconclusive. So we didn't have enough moisture in the air to really break up the pollen, but we found that if we had a wind mechanism that could be responsible, lightning could be responsible, even a rapid temperature change. All of these things have been proposed by different groups, mainly in the UK over the years. We still think probably it's moisture, but we're not really sure. But definitely more work needing to be done there. And so I just wanted to show you some work that was recently done by a colleague in Iowa using biofluorescence. And so she's got an instrument that she can take out into the field and in real time get measurements of what's in the air. And I can't describe it in any detail because I've got no expertise in that area, but we found it was really quite exciting. And so the example that she's got in the 3 plots here are for some storms that occurred in Iowa in May 2019. And they were looking at oak pollen, so it wasn't grass pollen, but probably we think the mechanism hopefully is not too different. And she found that it was associated with rain. So if they had rain, if they had thunderstorms with strong downdrafts, they could then measure in the air lots of these fine particles. But it does give us the I don't know, the idea that maybe if we had one of these instruments running in Melbourne, because we know that we're a hotspot, we might be able to detect if something was going on. And we could certainly do some good science with it. And so Betsy came out here for about 6 months last year on a Fulbright, and she unfortunately arrived a little bit too late in November to catch most of the season, but hopefully that collaboration will continue. And then just finally, the interesting stuff that they're doing at the health department, they're trying to understand whether they can detect a thunderstorm asthma event as it's occurring by looking at the hospital data. So Jim Black, who's an epidemiologist, has led a team where they are looking at the triage records of the hospitals as they come in, all electronic these days, using natural language processing to pick out when it says asthma, breathing difficulty, those sorts of words. And then they count how often are those words appearing in that hospital. And if they know how often those words normally appear, maybe a few times a day, but if it starts bang, 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 starting to get breathing, 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 then it lights up and says, oh, this hospital's having an asthma event. And so they were able to pick up an event that occurred last year on the 8th of November out in the western suburbs. And there was a thunderstorm. We were able to sort of link it to the weather later on. And what they want to do then with this information is they see things starting to light up. Usually the weather normally would come from west to east. They can alert those hospitals downstream that, hey, there's something going on over here. You guys might want to know about that and, you know, prepare yourselves. So I think this is really exciting work. There's lots of other things going on in the health area. I'm not a health specialist, so I can't really talk to any of those, but if anybody's interested in following up, I can point you to people who know more about this. But a few things that are interesting, we had a workshop in March this year over at the University of Melbourne, and it was very multidisciplinary. So some of the people who were there from the health sector talked about case studies that they're doing to understand what are the factors that might have contributed to the deaths that occurred in that event. Understanding what GPs can do, what did they do, and what could they do when there's to prepare people or when something's going on. Could they help with the hospital? You know, the surge capacity means, can they leave their office and go and, you know, help in the emergency department perhaps? Understanding the clinical and biological thunderstorm asthma risk factors, particularly for the hay fever sufferers and asthma sufferers. We think back to the 2016 event. Most people who knew they had asthma were taking preventative medicines. The people who were caught out were people with hay fever who didn't know that they had asthma or were susceptible to asthma. And then finally, smartphone apps. And these have been available for a few years now. The Melbourne Pollen app and the Air Radar app, which is from the University of Tasmania, both issue both air quality forecasts, but also thunderstorm asthma forecasts. So if you have the Melbourne Pollen app, you can get your thunderstorm asthma forecasts there. So I think this is my last slide. Just wanted to have a couple of reflections on being part of this work and what we've done. It's really driven home for me the importance of partnerships, that this was a multidisciplinary development of a service. It's operated by several different partners working together. I think technology has really helped us here because we can exchange data quickly and easily. We can talk to each other on video, and we do. So it's essential, but it's also really interesting and rewarding. So I've really enjoyed getting to know people who work in the health department or who work on plant biology and things like that. It's been fantastic. And here's a photo of a workshop that we had in, I think it was 2020 before COVID. I think the early warnings have had a good impact on Victorians, but also outside of Victoria. So there's greater awareness in all of southeastern Australia, people in New South Wales, South Australia, Tasmania. Well, we think Tasmania is probably not at risk, but people are much more aware and taking care of themselves. And I would finally just say that I think there's a lot of opportunities for people like me in the weather and climate area to collaborate with other people in the health area. So we've talked about thunderstorm asthma here, but extreme heat, lots of good work going on there. Air quality, vector-borne diseases, even mental health. So these are all areas that are ripe for collaboration. And I'll finish there. So please protect yourselves this season.
I'll take my privilege and ask the first question. You know, I remember being surprised when that big event happened, you know, a few years ago, because I hadn't heard of anything like that before. So is the incidence increasing, and is that due to changes in the weather or changes in the pollen distribution or changes in the susceptibility of the population?
Probably all of those things. So the projections for climate change, it's a slow process, but is that there is likely to be more pollen around. So possibly that's a factor. Certainly more people moving into the city, more people being exposed. Asthma is a big problem in Australia. We're probably, as a population, a higher incidence of asthma than most of the world. I don't know why that is, but so all of those things are factors. Yeah.
The pollen distribution surface of the drops, and the drops are fine. You might be a mechanism of bringing a lot of pollen particles together where they might be rubbing against each other.
I don't know if anybody's looked at that. We think it's probably hydrophilic. So we think that the mechanism for the moisture is it soaks it out, and it's osmotic shock. Basically, there's too much pressure on the inside, and it eventually the pollen grain's got a little hole in it, and it sort of goes poof and bursts.
Has anyone actually looked at how the pollen breaks up with a microscope?
Yeah.
To see if it can-
Yeah, I should have went and got a there. You can find videos online of a pollen grain breaking up, and it's just a very quick sort of thing when it happens. So, yeah.
Can you tell us a little bit about your journey? How did you end up becoming a meteorologist and studying this? Where did you, are you a physicist by training or a mathematician? What's your
I'm actually a meteorologist by training. So my parents were physicists. I grew up in California. Always liked the outdoors. So I was going to do some kind of science. It was going to be some kind of outdoor science, oceanography, geology, atmospheric science. And it ended up being the particular university that I wanted to attend, University of California at Davis, had a good atmospheric science program. And I thought, okay, give it a try. And yeah, it was interesting. So, yeah.
well,
Similar work done.
A little bit in Queensland. Thunderstorm asthma is not so much of a problem there, but there's plenty of asthma, just normal asthma. So at QUT, Janet Davies and her lab, they're doing a lot of work with it, and she's one of the Australian experts on thunderstorm asthma. There's work going on in South Australia, as I think they're not quite sure how much risk they actually have. But New South Wales is the other place. So Charles Sturt University has done more in the past, but I think the Bruce Graham was the name of the academic who was working on it, and he's retired. So there's not that much, but by having this event to focus many of us, you saw that group photo. We've kind of coalesced a bit of a community in Australia who are working on it, and so that's been really quite rewarding. But it's very small. You would call it a niche thing, I suppose. Yeah.
Do you have a definition of where asthma begins and hay fever ends? Like my family get dreadful hay fever, all of them except that. But none of them have ever had an asthma attack.
I'm not expert. Yeah, it definitely. I'd say wheezing. If you're wheezing, that's probably asthma. But I'm not a medico. So Danny Satoros, who's really the heart behind our service, he's an amazing man. And he's a respiratory physician as well as a health department officer. He's done a lot of media and a lot of education around asthma. And so I'm just telling you, sort of at the surface of what I've heard him say. But, yeah.
Thanks very much for your presentation, Beth. I'm intrigued by the Southeast Australia on one hand, and the prairie states of North America on the other. But it appears to me on the surface have many similarities. And in North America, there's a much closer distribution of target cities that would be vulnerable. So why doesn't it not better there?
It's an excellent question. I'm not sure I have an answer for you. I guess probably the grasses that are there are not so allergenic. But yeah, I don't know. The case that probably has gotten the most attention was in Georgia, which is not, why Georgia, but I think the sort of subtropical latitudes, when we think about Kuwait, Israel, southern Italy, some of the other places that have had thunderstorm asthma, England doesn't count. It's definitely not subtropical, but the sort of latitude bands where you might have enough energy in the weather and maybe the right vegetation. But no, it's very mysterious. Yeah. It may be. Yeah. Yeah, that's right. I can only think it's probably the grass, different grass. Oh, why are we growing this allergenic grass? It's really great. The cattle love it, the sheep love it. Could we stop growing it? I don't know. Starting to get into political territory. Kuwait. I don't know. I don't think of it as a grassy place, but maybe it is. Yeah.
Last question, Mel.
Certain suburbs of Melbourne, it's a bowl shape, you can trap the pollen in and stuff more than 8 feet apart. Is that something that you look at with regards to the system or might consider?
We haven't looked at it. I think that's a big thing to maybe look at is, you know, if there's some pockets. We know the events that we've had tend to start in the west. I think Western Melbourne tends to have worse occurrence of thunderstorm asthma, but that's closer to where the ryegrass is grown. There's a lot of other pollen. Ask anyone who's in the city in the middle of pollen season with the trees, the plane trees have pollen that you can see in the air. And that can be very annoying if you've got hay fever. But no, it's a good thing to look at and see whether the topography is somehow constraining some of the circulations. And some places are safer and some places are less safe.